slope fields. Slope fields give us a pictorial representation of all possible solutions to a given differential equation. All of them. So this is not finding the specific solution. So a differential equation is when we're given the derivative and we're trying to find the solution. Well, if we were given dy over dx equals x plus 3, that means dy equals x plus 3 dx, integral of both sides, gives me y equals x squared over 2, plus 3x plus c. This is considered the general solution. Now, every single one of the solutions is what kind of function? This just happens to be a whole bunch of quadratic equations. Whole bunch of parabolas. All with different y-intercepts. Aha, yeah, because that is the y-intercept. So if I graphed all the possible solutions, I'd have a whole bunch of parabolas, right? So how could the AP test ask you to know things about this? Well, slope fields. You could be asked to sketch a slope field. Given a differential equation. And differential equations can be something that looks like dy dx. You could be given a slope field. So they're going to give you this picture, which you're going to see what these look like here in a second. And you'd have to draw a particular solution. To do that, you'd have to be given some kind of initial value. Thirdly, you would have to match a slope field to a given differential. Or you might have to match a slope field to a solution of a differential equation. All right, so let's start with how to sketch them. First one, sketch a slope field given the differential. So we have a differential, and dy dx is also another way of saying, I want a different color for this because it's so important. What is dy dx also telling you? That is the slope. So we can find the slope at any point. So if I pick, I'll say the point up here, negative 2, 3. So if I pick a point, negative 2, 3, what is the slope at that point? So dy dx at that point would be negative 2 minus 1, which equals negative 3. So at this point right here, my slope would be a negative 3. So let's see, that would mean down 3 over 1. So I'm aiming at that negative 1. Now we're drawing a slope field. We're just going to make a small mark to show what the slope would look like at that point. Now what would it be for negative 2, negative 2? Be the same, wouldn't it? For here, it'd be the same, because this one just depends on the x value. That would be the same. I'm trying to make them the same steepness. So any point with an x value of negative 2 would have a slope of negative 3. Let's go to negative 1, 3. dy dx would be negative 1 minus 1, which is negative 2. So it's still a negative slope, but not quite as steep. It would be pointed at 1. So it'd be looking that way. So notice I'm pretending like I would draw the whole line, which would have a negative 2 slope, but then I'm stopping short of drawing the line, just drawing a little segment. Okay, our next points all have an x value of 0. So let's start at 0, 3. My dy dx would be 0 minus 1, which would be a negative 1. So negative 1 slope would be down 1 over 1. So I'm looking at that point. Pretend like I'm going to connect the dots, but I'm not. I'm just drawing in the slope. When I get to x equals 1, my slope would be 1 minus 1, which is 0. Whoops. That's easy. That's a horizontal line. If I plugged in 2, I'd have 2 minus 1. I'd have a positive 1. What we have drawn is our possible f of x's. Notice what they look like. These are all going down, and then it goes back up. What kind of graph would this look like? Well, it looks like it'd be some kind of parabola. Zoop, zoop. Slope of 0 at that minimum. Okay, so let's try the next one. Ooh, this one has x's and y's. Great. So let's make a table using our points. And you could actually make a table like x, y, and then this would be dy dx. So let's start with negative 2, 3. So negative 2, 3. This says I'm going to take the x minus the y value. So I get negative 5. Ooh, that's really steep. This one would go 1, 2, 3, 4, 5 and point to that point right there. Now if I had a ruler I could do really good with this. But I don't. Ooh, that's pretty good. The next one would be negative 2, 2. So that'd be negative 4. So 1, 2, 3, 4. Still looking at that same point. So the next one would have a slope of negative 3. The next one would have a slope of negative 2, negative 1, and 0. Here, my point is negative 1, 3. So let's just go ahead and go to that. Negative 1, 3 would be negative 4. So starting here, 1, 2, 3, 4, it'd be looking at that point. So it'd be going down like this. Notice the next one would be a negative 3, negative 2, negative 1, 0. But down here it would turn into, so if I had negative 1 minus a negative 2 would be positive 1. This point is 0, 3. So 0 minus 3 would be a negative 3. Negative 2. Negative 1. 0. Positive 1. positive 2. This point is 1, 3. So 1 minus 3 is negative 2. Negative 1. 0. 1. 2. 3. This point would be 2, 3. So 2 minus 3 would be a negative 1. This would be a 0. 1. 2. 3. This would be a positive 4. Okay, so what if we were given the slope field? Oh, this is one we've already done, huh? We developed it for dy over dx equals x minus 1. What if we were asked to sketch the solution curve that goes through the point 1, minus 1? So it's going through the point 1, negative 1. Since dy dx is linear, the solutions should look like parabolas. So how would this look? Well, over here it's going to have a steepness that's like that, right? Right at that certain point. So it's going to be kind of like this. And it'd be the same thing right there. So notice these are giving me my steepness as I get to that point. Here it's going to be a lot steeper, so it might be it's getting close to that steepness. It's that steepness right there. And then it's going to keep going. It's going to get that steep right there. So we're wanting to match those slope curves. And we have parabola. Oh, this is a fun one. Match the slope field with the solutions. So remember, this is the original function. This is the derivative of it. So take a minute and see if you can match them up, and then I'll talk about which ones went with which. Now, one way you can do this, by the way, is to think about what y might have been. So I find that helpful. So I'm going to go through in all of mine and go, well, if dy dx is sine, then my original was negative cosine x plus c. This one would be x squared plus 4x plus c. This one would be 2x plus c. This one would be e to the x plus c, and so forth. So I sped up time and finished the rest of them. So the easiest one I feel to find is going to be our slope field that was just all the slopes are 2. We have lines with a slope of 2x. So when I look back over here, looking for one that has constant slope the whole way through. Well, that would be J. Now I have several that have quadratics. So those may be a little bit harder to find. So we need to think about some things we might know about quadratics. For example, x squared plus 4x. It would have its vertex, its max or min, at negative 2, which is also be the solution of 2x plus 4 equals 0, or if you use negative b over 2a. So its vertex would be around negative 2. So let's see. This one looks like a parabola. What else? Well, this one looks like a parabola, but it's upside down. This one kind of looks like a parabola, and all the vertexes, even though some of them are higher up than others, the vertex has an x value of negative 2. So this is A. Whoops. Now there was one that was a parabola that looked like it was upside down. This one. And it had a vertex at +2. Let's see, upside down parabola. Ooh, there it is. This is really -x² plus 4x plus c. That's it. Then there was a parabola that went right down the y-axis. F. That would be this one, x² plus c. That is, which one was it? F. All right, so we've gotten some of these narrowed down. Now let's look at some of the others. This one looks like it kind of goes up like this. That looks kind of exponential. Let's see, did we have an exponential function? Oh, we did. Here he is. B. So we found B. Look at the next one. These are negative, and then it goes, so this graph is increasing here, leveling off, and then increasing. Oh, let's see. Do you know what function would look like that? Would look something like this. Ooh, that's cubic. That is definitely cubic. Oh, that looks like number 9. 9 is a cubic function with its turnaround point at 0. Cool. Oh boy. Okay, so we've got several more to look at. I'll try to mark them off as we find them. D. Okay, so D looks like it's going up, down, up, down, up, down. Okay. This looks like a what curve? Which one starts kind of in the middle of a hump? Well, that sure looks like sine to me. That would be sine. Ooh, E I'm not sure on. Let's pretend I'm not sure on. Ooh, here's another one that looks kind of curvy. Curvy scurvy. It's doing up, something down, something up, something down. Looks really curvy like that. Oh, I looks like an upside down cosine. Okay, so we're left with these two. This one has a negative slope here, and then it turns around, goes up, turns around, and goes back up. But notice how it doesn't slant off. This one just goes straight up, really, really steep. That looks like an x to the 4th. It is. There's an x to the 4th. So that means this last weird one, what would that graph look like? Well, it looks like it starts off, comes in, and goes something like that, and then somehow on this side it's doing something like this. I wonder if that has something to do with ln x. But absolute value of x, that's why we got those two sides. The next one has slope fields, and we're figuring out the solution that goes with it. Exactly what you did before. So the slope fields should look like the y's. They should look like y. So I'm going to pause my video and then let you have time, you pause too, figure out which one goes with what. Okay, so just to show you, I kind of sketched in what I felt like y was going to look like. And then I start to match them up. Well, y equals x is a straight line. That matches C. Y equals x squared is a quadratic. That's A. E to the x. E to the x looks like this. Ooh, that kind of matches F. This one don't know off the top of my head, so I'll come back to it. X cubed looks like this. That kind of matches the picture of H. Now I had two that look like they could be sine or cosine, so I'll come back to those as well. Let's see. Ooh, this one doesn't exist when x is negative, and it just does something like that. So look at J. 10 is tangent, and tangent is that crazy looking thing that does that, and it repeats itself over and over, and that looks just like I. Ooh, forgot about y equals 1. Y equals 1 is a horizontal line. That's got to be G. So cosine and sine were the two curves, and I know that's got to be either B or E. This crazy one is 1 over x squared. So how do I figure out about my derivatives? I mean, which one matches? So I know these are the graphs of the slopes, right? So let's figure out what dy dx would be for each of these. Well, that's cosine x. And this one would be negative sine x. At x equals 0, what would be my dy dx? Well, it'd be negative sine of 0, which is 0. Over here, cosine of 0 is 1. So I can tell the difference by looking at the slope when x is 0. When x is 0 here, it looks like we have a positive slope. When x is 0 here, it looks horizontal. So this has got to be the one that had a slope of 0. And then this was the one that had a slope of 1. So we'll do the practice problems. I want you to start working on those, and then we will do the rest in class.